So our speaker today is Christopher Parrish.
Woo!
So Chris is a professor and a Plasker faculty scholar in geomatics at Oregon State University, where he also serves as a director of the Geospatial Center for the Arctic and Pacific. I don't need to.
I can also introduce myself. I know.
Okay, please go.
All right. Hi, everyone. I'm Chris. How was that? Good. It's really an honor to be back here. Thank you all for inviting me to come back and give a CCOM seminar. And it's just so nice to see so many colleagues and friends. I'm also really glad to talk about the topic that I was asked to present on today, which is a little thing called solving the nearshore coastal data void. So this is a small task I want to do, solve the global coastal nearshore data void. When I say I really mean we, for a number of reasons, and we, like we. This is too big a problem for any one person, and also I really like collaborative research. I don't like doing things myself, so this is a topic that just invites collaboration. So I'm going to present this, and if there's time at the end, of course, in the QA, you all can ask me questions, but maybe we can spend some time just brainstorming about how to do this. And if you don't believe that there is a coastal nearshore data void, I'm going to start by trying to convince you that that is indeed a thing. Just really quickly, before I get into that, I wanted to talk about where I am and our center at Oregon State University. So I'm here from Oregon State University. Previously, prior to that, I was here at CCOM, and before that, I was a NOAA person. So at Oregon State University, we're really fortunate. We were one of 4 universities that got a NOAA National Geodetic Center Geospatial Modeling Grant. And so our new center is called GCAP, the Geospatial Center for the Arctic and Pacific. We've got 2 main thrusts. The first is research. So we've got 6 different research projects, 6 different task leads, grad students working on these. And it all has to do with helping the National Geodetic Survey and modernizing the National Spatial Reference System, or NSRS. So you might have heard that in the next year or so, NGS is going to be producing 4 new terrestrial reference frames and a new geopotential datum. So get ready for that shift. We're doing a lot of work, a lot of GNSS research that is aimed at helping NGS. And if I get to come back here and do another CCOM seminar at some point, I'll be really glad to talk about that GNSS work. For today, I'm going to try to stay on topic and talk about nearshore bathymetry, which is also near and dear to my heart. The other main component of what we do at GCAP is there's a large education component. So this is geared towards being able to develop the next generation of geodesists, surveyors, geospatial professionals. So there's a heavy outreach and education component to what we do. So that's GCAP. Just really briefly, these are our graduate students. We're up to, I was so surprised that I went to lunch with the grad students here today, and thank you all for going to lunch with me. I was really pleased to see how big the grad student community here has grown. We've also got a lot of grad students. We're up to about 30, all just fantastic students. Some of the work that I'm going to present today is by folks who are in this photo here, and I'll try to call attention to them when that time comes. So first of all, what if you don't believe me? What if you say, Chris, nearshore data void? There is no nearshore data void. Well, what do you think? If you look at a map like this, it's easy to think that this thing that I'm telling you is a problem is actually not a problem, right? Does anyone see a nearshore data void here? It might be because you're too far away. You could come, if anybody wants to come up here, you can stand right here and look and see if you see a nearshore data void. You won't. You won't, right? And the issue is scale. By the way, this is a fantastic product. This is the JEPCO 2022 data set. I know there are a number of JEPCO folks here at CCOM. I'm a huge fan of the JEPCO data products. The reason you can't see data voids here is just too small of a map scale, right? This small map scale means big area on Earth displayed on a small rectangle. Well, there's also the issue of map distortion. You can't take the whole world and display it on a flat plane without getting some distortion here in the northern latitudes. But no nearshore data voids that we can see, right? So what do you mean nearshore data void? Well, what happens if we zoom in? What happens if we zoom in on best available data sources? Immediately we start to see a problem. Here we've got a couple areas in Alaska, one area in the Channel Islands off the coast of Santa Barbara in California, And we can immediately see there are these areas of data voids, data gaps, just these areas that say no data. But I don't know, maybe things are okay. There's only 3 areas here. Maybe I scoured the ends of the earth, looked at all available data sets, and I just found these 3 examples. I'm just gonna say Tom Lippman's not here, is he? Just gonna use him as an example. Tom's got a jet ski, right, with a multibeam on it. I was gonna say, maybe we could borrow Tom's jet ski and in a couple months, we'll go solve this problem. All done, just 3 areas, right? Agree? Except, whoops, I lied. It's not just 3 areas. Here's 6 more. We're up to 9 examples of these coastal regions. This one I like. This is a raster nautical chart. So we see these 2 areas that say unsurveyed, and then there's this really helpful message that says that these areas are constantly changing. That wouldn't give me a ton of confidence in navigating in that area. Next to it is a ENC, this one also Southern California. So we're up to 9. We might need to borrow Tom's jet ski for a little while longer. We might need it through the fall. Except, oops, here's some more. And guess what? I could keep going and going. I could do this all day. Why? The answer is because these nearshore data voids are everywhere. All of these examples that I've just shown you are just here in the US, and the US is pretty well mapped compared to a lot of places on Earth. So you start looking globally, and you will find this nearshore data void everywhere. So what do we do? Before I get into how we're gonna solve the problem, maybe let's spend a minute just talking about why it exists. So what causes this global nearshore data void? One of the reasons is just this is hard, right? How do you get data in these areas? If you look at conventional surveying technologies, things like total stations and GNSS, those aren't designed to work underwater. There is something called GNSS acoustics, but that's very expensive, not readily available. So if you look at these conventional surveying technologies that are used for land, you're gonna try to use them for doing bathymetry, you're really limited to just the very shallowest regions where somebody can stand with a survey rod, right? And then if you start talking about boat-based surveys, those can be useful, but I think, as a lot of you know, multibeam, as you start getting shallower and shallower, it becomes less and less efficient, right? And then you've also got the challenge that, if you're putting either people or small boats in these nearshore areas, you could have dangers like breaking waves, surf, rocks, kelp, seagrass. So it can be dangerous. And in fact, this is the reason that NOAA established something called the navigable area limit line. Out of curiosity, anybody here a NOAA Corps officer or survey tech on a NOAA hydro survey ship, sailed on a NOAA ship? Okay, a few. So for those who have been on NOAA hydro survey ships, you're familiar with this. No, right? Basically, this is a line that it basically establishes the limit of where you can survey. So if you're a NOAA survey ship or launch, you need to stay offshore of this null. And where is the null? It's at least at the 3.5 meter depth contour, but it can be further offshore than that, depending on the scale of the largest scale nautical chart, and then at the discretion of the CO. So if the commanding officer says, hey, there's kelp or breaking waves, they can push it even further offshore. And what does that do? Well, let's look at an example. So this is Vieques, Puerto Rico. I've never been there. It looks beautiful. So this is an island off of Puerto Rico. We're looking at the north side. Anybody been here? Oh, awesome. Cool. So you all can tell me much more about this. This is actually a national wildlife refuge, which is why this area isn't built up. And what we're looking at is a topo bathy airborne bathymetric lidar data set that actually does cover this area. So if we look at this, if we look at where the 3.5 meter depth contour is, it's right there. So at a minimum, we're probably not getting any data in this region. And the reason I asked if anybody had worked on a NOAA hydro survey ship, my best guess, I was going to ask for confirmation of this, but my best guess is that where they would actually put the null in this case is probably not here, but at the outer edge of this reef right here, which would create even more area of no data. So let's say you're this ship right here. You're the captain of this ship. You might say, who cares? Who cares? If you're the captain of the ship, you're not going anywhere near here or here or here, right? You're gonna, if you even try to get close to this area, you're gonna be in a lot of trouble far before you get there. So that begs the question, why do we care? And I'm gonna tell you, I know this for a fact. I mean, I work with people who have a critical need for data in this area. And who are these people? One of the first ones, I put this one up top here, small boat operators. There are some people who would disagree with me on that. I've heard a statement, I've even heard a statement maybe in this building that small boat operators aren't often using nautical charts, maybe don't even know how to use nautical charts. I'm sure that's true in some cases. Any of us who have been on the water or even been at the local boat ramp have seen people who are out there causing all kinds of trouble, don't really seem to care much about safety. And I'm sure those people are not really paying too much attention to nautical charts. That's almost the least of their concerns. But I think it's a bit unfair. I certainly know small boat operators who are extremely safety conscious and are definitely looking at chart data and will probably rely on it even more if we could give them better data in those nearshore areas. So I've got that as number one. Number two, marine ecologists. And I'm going to talk later about some outstanding work with Jen Dykstra in the Florida Keys. So understanding climate impacts on coral reefs, for example. The third one, coastal zone managers. I was just talking to Larry yesterday. Maybe I should just call that coastal managers and policymakers. So things like, I've got a great example. I won't tell the story, but I've got a great example of working with Tim Batista and Noah Incos, and the data that we collected being used by coastal managers in establishing marine protected areas and then evaluating the effectiveness of those marine protected areas over time. Also establishing hurricane and tsunami evacuation routes. So being in the Pacific Northwest, that is a huge concern. I don't know, anyone been to Oregon, been to the Oregon coast? Yeah, so Gabby, you were just there last year. So beautiful area. You saw these I think we stopped and saw some of these hurricane or tsunami, tsunami evacuation warning signs. So about every 300 years, there is a Cascadia megathrust earthquake and potentially a corresponding tsunami in the Pacific Northwest. It's been 324 years since the last one. So this is certainly a concern for us in the Pacific Northwest. So establishing evacuation routes, physical oceanographers doing things like modeling storm surge, and marine geologists studying nearshore processes. So how do we do this? I'm going to suggest that we look to space to see if we can solve this problem. That might seem strange, right? Rather than looking for things that operate on the water or here on Earth. The logical question that you might ask is, why do this using spaceborne technologies? There are a few reasons. One of them is that I said in the beginning, we want to solve this problem globally. And there are areas, if we want to do this globally, there are coastal areas that are so remote that it would just be hugely expensive to try to send a person, a boat, an airplane. This is an example I love, Manihiki Atoll in the South Pacific. I've showed this example before. I love it so much. This is just Google Earth. I love this because if you look at this sort of view of Earth, you almost wouldn't recognize this as Earth, right? It looks like a planet that is all water. So we're looking at Manihiki Atoll is part of the Cook Islands in the South Pacific. If you needed to go there to map and get a boat out there, that would be just hugely expensive. And there are a lot of areas like that. So satellites, one of the things they do is they give us near global coverage. And then the second thing they do, and this is really important, is depending on the revisit cycle, you get many, many opportunities to pass over that same area again and again and again. And the reason why that's so important, a lot of the technologies that I'm going to talk about today depend on having good water clarity, meaning you can see a good distance through the water column. Water clarity in a lot of places is highly temporally variable. So you can have a satellite overpass where you overpass and it's turbid, another overpass, turbid again, another overpass, turbid again, and then on the fourth time, you just happen to hit that at exactly the right time, whether it's the stage of tide or the season or whatever, and you've got great water clarity. So that's also really important. All right, so that brings us to probably the main technology that I wanted to talk about today, which is NASA's ISAT-2 satellite. This was launched in 2018. It was actually really cool. I got to go to the launch with my daughter, who was in 7th grade at the time. That was a pretty amazing experience. This is true. I've said this at Geomatics. I think maybe Brian has heard me say this, but absolutely true story. ISAT-2 launched, and so I'm watching it go up, and I yelled up at it. I said, "Go get some bathymetry!" and then a few months later, I started seeing the bathymetry from it. It was amazing. But it was the thing is, it wasn't designed for bathymetry at all. Ice is in the name, right? So it's designed for cryospheric science, monitoring ice sheet thickness, land ice, sea ice. Also global vegetation heights, but not really bathymetry. Just briefly to tell you about the satellite, so it's the orbital altitude is about 500 kilometers. It's got 6 beams. Let's see if I can do this. So basically it's 3 pairs of beams. So a center pair of beams and then 2 that are out to so about 3.5 kilometers out on the ground. And so along each of those tracks, you've got two beams. Within each pair, it's 1 strong beam and 1 weak beam with an energy ratio of about 4:1. And so, and then along each beam track, you're basically pinging. So it's not a scanning system. You're not getting a swath. You're just getting these 6 individual, like ping, 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 like that. And then that distance between spots is about 70 centimeters. And it comes back to the same place approximately monthly, with a 91-day repeat orbit. So even though ISAT-2 was not designed for bathymetry, there were 2 design decisions that led to it having pretty significant bathymetric mapping capability. One is that its wavelength is 532 nanometers. That's the same wavelength used by all but one of the commercial airborne bathymetric lidar manufacturers. It happens to be good at penetrating water. The second design decision that led to, oh, and by the way, initially they weren't even sure if it was going to be 532. So NASA initially was thinking it was either going to be 1064 in the near infrared, or it was going to be 532. If you're good at math, you can figure out that one of those is exactly half the other, right? That's not a coincidence. It's because they put a frequency doubling crystal in front of it and turned 1064 into 532. Or it was going to be a combination of those 2. And so there were about 3 main moments in the ISAT development history. I already told you about the launch and how exciting that was. I was also super excited. I remember kind of doing a dance for joy when I heard for sure that it was going to be 532 nanometers. And along with a student that some of you know, so Nick Forfinsky-Sarkozy, who was a master's student here once, he came to do a PhD with me. And even before launch, Nick and I were looking at ISAT-2 and we were trying to figure out, is it going to be able to map bathymetry? And we really thought it was. We had no idea how well, because there were a lot of parameters that we just didn't know. But the day I heard that for sure it was going to be 532, I remember doing kind of a dance for joy, thinking, all right, it's gonna get bathymetry. So that's one, and then the other is that it's photon-counting technology. And so if you look at the ISAT-2 photon clouds, and that's what we're looking at here. So each one of these dots, this is like a vertical slice, right? The along track direction is that way. Each of these dots is a return. And you look at this and it looks kind of noisy, right? It looks like it's snowing. That's a characteristic of the photon counting technology, but this is actually good for us because it's really sensitive, and therefore you can get these weak seafloor returns, and it will actually measure a return. So basically what we're looking at here, I'll show you another example in a minute. We've got a profile where here's some points on land, here's water surface. If you actually zoom in, you can also see the water surface waviness, and then you look down below that and you see this clear sort of bathymetric trace. This launched an entirely new field of study. According to Google Scholar, and I never know how much to read into these values, but if you open Google Scholar and you type in ISAT-2 in quotes and bathymetry in quotes, as of 2 days ago, that gave you 470 results. So something that, space-based bathymetric lidar 6 years ago was not a thing, and now it's a thing that there's a huge number of published papers on. So kind of cool. This is just an example of a profile. So kind of same thing, we're seeing some of the points over here on land and vegetation. Then we've got the water surface, and then these are all seafloor returns. You can see that in some cases, well, it kind of depends. This is something my students and I talk about a lot. Where do you all think this bathymetric trace ends? Is it here? Well, thoughts? Did you go with all the way down here?
Yeah, sure.
Whoever labeled it did. They drew it all the way down to here. Maybe that's right. Humans are such good pattern recognizers that we tend to see patterns even when they're not there. So I think there's a little bit of danger. But regardless, we're going at least like 30 meters. This is not refraction corrected. The refraction correction is going to move these points up a bit. I'll talk about that later. But anyway, pretty amazing. Pretty amazing. If you want to know where ISAT2 bathymetry is going to work, this is a tool developed by a colleague, James Dietrich, who's at he was at University of Texas at Austin, working with a colleague of mine, Lori Magruder. I'll say more about Lori in a bit. So James Dietrich developed this web map that is really quite cool. So this is just to give you an idea. If you want to see where and when ISAT2 bathymetry might be useful, basically what James did is he took best available Katie is diffuse attenuation coefficient of downwelling irradiance. It's a measure of water clarity. So it's like a global measure of water clarity. So he took that data and sort of best available global bathymetry, and he created this map by, for each area, how many months per year might we be able to get ISAT2 bathymetry. The other thing that's cool about this is it works for other things too. So NOAA has a tool called SatBathy that they use for generating bathymetry from multispectral satellite imagery. This also works really well as a SatBathy feasibility tool. So like when and where is this going to be feasible? So this is online. You can go see this if you want. Another thing that we did, this was also something that James Dietrich led, and it came out of, we've got a really cool ISAT2 bathymetry working group. Jen calls into this sometimes, Kim Lowell calls in. I think they're pretty fun. We've had a few discussions that have actually led to published papers. They're things that we just start talking about, and before you know it, we've got a study and a paper. So one of them was this. In the early days, well, the first few years of ISAT2 bathymetry, we were actually missing bathymetry because it was being clipped by the satellite. So there's this thing called the telemetry window. And the best way I can describe this telemetry window is it's a vertical band that it controls the amount of data. Like what is the size of that vertical band that's gonna get not just recorded by the satellite, but telemetered or sent down to the ground. And there's a limit to that, right? You don't wanna, if you're sending too much data down, that's going to be expensive. You're going to eat up all your bandwidth. You can't do that. So there's a volume limit. And so in the early days, they had this window set too narrow. And so there were areas where actually we should have been able to keep measuring bathymetry, but because of how that telemetry window was set, we were missing bathymetry. So we did this analysis and kind of figured out how we might open this, and the telemetry window, the NASA ISAT2 algorithms team worked to broaden that telemetry window, and guess what? It worked. We were able to show, so here's an example. This is the same area. So this is before that telemetry window change, and now we get that profile all the way down to here, and the comparison, the blue versus red, that's just comparing it to best available reference data. But that approximately doubled the amount of area that we can get with ISAT2 bathymetry. So it increased it by 6.1 million square kilometers. So that was pretty cool.
Hey, Chris, can I ask a question?
Yeah.
On that last slide?
Yeah.
What is the echo like below the seafloor?
Yeah.
It looks like a multipath, but the distance doesn't make sense. You
do see that. So let me tell you what it actually is, and then I'll tell you what it looks like. What it actually is this. This is the so the blue is the refraction corrected, and the gray down here is the non-refraction corrected. So basically what happens is the ISAT2 algorithms don't know when that beam enters the water column. So they're not accounting for the fact that it's bending in, and they're not accounting for the fact that it's slowing down by about 33%. And so what ends up happening is that when you apply the refraction correction, it's moving points up by about 25% of the water depth. What was I going to say about this? Yeah, but you do actually sometimes see ringing. And so if this had been the actual bottom detection, and then we saw this little trace down here, that would have been feasible too. That would have been ringing that can sometimes occur. We see that more with the water surface return just because it's so bright. Thanks. Anyone could stop me at any time. I should have said that earlier. Yeah.
What is the cross-track resolution?
Oh, Great question. So the distance between each pulse in the along track direction is 70 centimeters. So pretty small. But in saying that, I also like to point out that each individual beam size, the beam footprint is about 11 meters. So you like imagine an 11 meter spot right here, and then I go, how far would 70 centimeters be? You know, maybe something like that, and then another 11 meters.
That's at the sea surface.
Yes.
And how far does it spread when it enters the water?
Oh, good question. You and I have talked about this, right, Larry? We had an experiment once. I wanted to build this thing over here. I don't know the answer to that.
It's still unresolved. I mean, the rule of thumb is half the water there.
So you see these cartoons, anyone who's studied airborne bathymetric lidar, you see these cartoons where the pulse enters the water column and then it flares out. It does this. But I don't see it. I've stood in the wave tank over here with a green laser pointer and pointed my beam down, and I can't see an appreciable difference between the size of that spot where it's on the water surface and where it is on the seafloor. And is that just because this is freshwater? And here, if we could fill the tank with seawater, and this is the thing that I proposed to Larry, and for some reason he told me no, I couldn't. And so then we were gonna build a dedicated tank, and that fell apart too.
Yeah, no, but it's amazing, you know, there's this rule of thumb, but it's not based on anything.
Well, I mean, I should show you another presentation. To an extent, we have studied this. We have studied this because in the work that this is another collaborative project between OSU and CCOM, of course. So CBLUE is airborne topobathy TPU, total propagated uncertainty software. So we have this software called CBLUE that's been developed over a 6-year effort. It's CCOM, my research group, and NOAA and GS. And so one of the things that we do in this CBLUE is we model using Monte Carlo ray tracing and some code by Kurt Mobley, who's an optical oceanographer, sort of model where these rays go. So you have rays that, first of all, they encounter the water surface, and then they go in different directions based on whatever wave facet they encounter. But then they have some number of like random scattering events that occur between the sea surface and the seafloor. So they end up somewhere on the seafloor, and that's actually what we're modeling and using. And so if you believe the simulations that we're getting, a beam size that starts at about 2 meters on the water surface, by the time you get down to 10-ish meters, what was your rule of thumb? Like
Half the water depth.
Half the water depth? Yeah.
So if you're in 10 meters of water, you know, a two meter laser footprint, typical bathymetric laser, by the time you're at 10 meters of water, it'll be a 5 meter footprint.
It's close to that, a little less, not quite that large, based on the modeling. Others? We can just talk about, I can stop the slides and we can just talk about stuff. Back to ISI2, another question I get is how accurate it is. There have been a lot of studies. This was based on some fairly early on analysis that we did based on Gleason in 2021. I'll just tell you all, some of the studies that have been done on ISI2 accuracy, I'm not sure I totally believe the methods. I'm not sure that I believe that the reference data that they're comparing against is all that good, and when they don't talk about atoms and coordinate systems and transformations, I can be a bit skeptical. One of the people who have done this well, and that I believe, in water flows go up to about 20 meters, kind of an average RMSE is about half a meter. So if people just want a rule of thumb estimate, I tend to say about half a meter, 1 sigma, and that's pretty good, I think. Certainly not rivaling what you can do with multibeam or airborne bathymetric lidar, but from a space-based technology, I'm impressed. Here's another thing that you can do, and this is another way in which ISI2 bathymetry is useful. So one of the limitations, the two biggest limitations of it, I would say, are this. One is that, like airborne bathymetric lidar, it only works where you've got clear water, so water clarity, probably number one. And then the other limitation is that it's only giving you data along these discrete track lines. So if you want wall-to-wall coverage, you've got to combine it with something else. So the thing that a lot of people have done, and I've had a couple students work on this, but many other people have worked on this too, it's combining data from an imaging sensor, like Landsat or Sentinel-2, with data from ISAT-2 to get wall-to-wall bathymetry totally from space. And the reason this works is that these technologies are complementary. So bathymetry estimation from imagery, this goes back, people don't believe me on this, bathymetry estimation from imagery, I've got a paper from the 1940s where people were looking at estimating bathymetry from aerial imagery. Much more recently, since the launch of, or since the start of the Landsat mission in 1971, I think, what's called satellite drive bathymetry, SDB, has really come a long way. But it's a very indirect method of measuring bathymetry. You're basically just, it's not like, I mean, the most direct method of estimating bathymetry, you're standing out in the water with a sounding pole, or you've got a lead line or something like that. Sonar, still pretty direct, airborne, lidar, pretty direct. By the time you get to estimating bathymetry from imagery, it's just an estimate and there's a lot of other confounding variables and you need some data to train it. But it does give you contiguous coverage. So if you take that contiguous coverage that you get from the imagery derived bathymetry and combine that with ISAT-2, which is only along the discrete tracks, but it is a more direct measurement of bathymetry, now you get purely from space, totally from space, contiguous bathymetric coverage. There's, I'm so gonna run out of time. How long do I have, Daniel?
If you want.
As long as I want, okay. All right, I'm gonna keep talking. I'm gonna keep talking then. There's an issue though. There's an issue. I just said that, you know, you put these two things together and it gives you contiguous bathymetric coverage, but too much so. When you do this, when you run bathymetry estimation on imagery, you've got an algorithm, right? You put in an image, what you get out is for every single pixel in that scene, you get a value. Is that value actually a depth? No. It could be optically deep, it could be a boat, it could be a boat wake, it could be a cloud, it could be land. Some of that you may have masked out, but there's a lot of reasons why you can get values that aren't actually bathymetry. So I've had another student, a NOAA Corps officer, Matt Jere, who graduated last year, who did this whole project that we called bathymetric truthiness. Maybe I'll get to talk about that. Since Larry said I've got all the time in the world, I can tell the story. So Matt.
You keep talking as you want, we're gonna get up.
Yeah, you'll be fine.
You just keep talking.
That'll be fine. That'll be fine. I can stay in here and talk to myself about Nearshore bathymetric mapping. So Matt last year was doing this. Matt was doing, I called it bathymetric truthiness. He just got his journal paper published. The journal reviewers didn't like bathymetric truthiness. We had to change that to something else. But I had another student who sat right next to Matt, Forrest Corcoran, fantastic PhD student. Forrest was doing something that, this was my term, not his. I called what Forrest was doing deepfake bathymetry. It wasn't really deepfake bathymetry. It was using deep learning to try to fill in gaps. And ISAT-2 bathymetry. But I just thought it was funny that I had two students sitting right next to each other. One was doing bathymetric truthiness and the other one was doing deepfake bathymetry. Both fantastic. I got way off track. This is, you know, putting these two things together. And when you do this, you can create contiguous bathymetric maps like this. This was yet another former student, Ben Battle. So Ben, among other things, created this web GIS called Shallow Bathymetry Everywhere. That's a misnomer. I haven't updated this in 2 years now, so we only have 13 sites. So it really should say Shallow Bathymetry in 13 places. But kind of cool, kind of cool. You can go download this. Getting to ATL 24. So at the end of ISAT-2's nominal 3-year mission, it entered an extended mission phase. It's got enough fuel now for approximately another decade, which is good. So along with a fantastic colleague at University of Texas at Austin, Lori Magruder, Lori and I were fortunate to get funding from the ISAT-2 Project Science Office to develop a new ISAT-2 bathymetry data product. And the reason this is important is up until this point, there hasn't been a dedicated bathymetry product. There's an inland data product developed by Mike Jasinski and company that's very good, but nothing specifically for dedicated to bathymetry and the coast. So this is what we're doing, and we're doing something new that I think is really exciting. Unlike all the other ISAT-2 data products that are kind of like static products, so they get generated periodically, but then it's like a static product that sits on a server that you can go and download. We're going to create this using a web-based, a NASA web API called SlideRule that is going to enable cloud-based processing. And so users will be able to go and ping this either through like a web map interface or through their Python code. And actually, in the second version of this product, they're going to be able to customize things. So you'll be able to pick what parameter settings you want, not just your AOI, but if you want to do something different with the refraction correction or different parts of the algorithm, you can tweak things. So super excited about that. The team it's Lori Magruder's team down at UT Austin. So Jeff Perry, Matt Holloway, Jonathan Merkel at OSU, Kiana Key, Forrest Corcoran, Ellery Ohlweiler, and then from NASA Goddard Space Flight Center, JP Swinsky, and a few others working on this. This is a fantastic team. This is the workflow. I'm not going to talk through this because there's a lot of boxes here, but I just want to tell you generally what we did. So this is all about like reading in the data and doing some pre-processing. All of this right here, this is all about classifying the bathymetric bottom and classifying the water surface. And as you can imagine, that's a huge part of the problem. We really have to get that right for this to be a good data product. So that happens. After that, there's a refractive index correction, a final sea surface finder, there's an uncertainty calculation that I'll talk about, and then we output the products. And so you get in a variety of formats, there's about a half dozen different file formats that you can pick. And so you get out these attributed point clouds that have water surface and bathymetric bottom output, refraction corrected bathymetric bottom, ellipsoid heights, orthometric heights, refraction corrected latitude and longitude, and some other ancillary products. Really cool. One of the other things that I like about what we're doing is this ensemble approach to classifying the water surface and the seafloor. So I don't know if anybody here does any ensemble learning. Kim Lowell probably does. So what happens here is it's basically we've got all these different base algorithms or models, some developed by our team, some developed by others, but they all do things differently in how they classify the sea surface and the bathymetric bottom. And that's important. We don't need any one of these to be perfect by itself. What we need is for them to do things differently, because then we put them together into the ensemble model, and the ensemble, like the whole is better than the sum of the parts. So we can do a better job using all of them together. And that's how we get our final sea surface and bathymetric bottom. Just quickly, some other things. So 3 of my students, as part of this, we had to develop a training and testing database. So we went to over 100 sites around the world looking for different coastal morphologies, different substrate types, different cover types, and hand-labeled water surface and bathymetry. So I had 3 students do that. Ellery Ohlweiler led it, and we published that. So other people can get this and use our SAM training and testing database if they want. And thanks to, I don't see Larry Ward here, but Larry helped us with the classification of the geomorphology of these sites. This was important. This was a non-glamorous part of the work, but something that I thought was important. We had to develop a mask. So the mask basically determines where we look for bathymetry. There were a lot of options. We didn't have to use a mask at all. We could have just let it look for bathymetry everywhere. I thought a lot about that. The reason we ended up not doing that is it's hugely computationally expensive, and that translates to actual money. It also would have resulted in false bathymetry in different places that we would have had to edit out. But so we want to limit it, and we can do things like not look for bathymetry in Kansas or over the Mariana Trench, where there is bathymetry in the Mariana Trench, but it's 11 kilometers deep or something. We're not going to map it with ISAT-2. So we wanted to limit it to the realistic area, but we didn't want to limit it too much. And there were several meetings where nobody was disagreeing with me, but to be dramatic, I pounded my fist and said, we do not want to miss the opportunity to discover previously unknown bathymetry. So we buffered it anyway. This is what we've currently got as far as our search mask. Refractive index.
Is it simply a depth criteria?
A depth criteria, yeah. So this was using best available bathymetry, and what else went into this? There were a few things that went into it, and then we ended up buffering it both vertically and horizontally. So when I say buffer vertically, we went to 1 psyche depth, and then we went 2, 3 psyche depths beyond that, and then that gave us an area, and then we buffered it out about 300. Oh, maybe a kilometer. I can't remember, but
So it was a 3 consecutive criteria, basically. shallower than 3
Yeah,
seconds.
and then buffered horizontally. This is our refractive index layer. Interestingly, this thing never existed, so we're getting ready to do a journal publication on this. But people out there, the airborne bathymetric lidar, you don't need to do what you do in multibeam. In multibeam, you really need to do, like, those of you who've taken the ocean mapping class, you've got like this stratified, like this layer cake, and you've got to do ray tracing and figure out where each of these beams go on the seafloor. You don't need to do that in bathymetric lidar, but you definitely do need to account for how the light bends at the air-water interface and how much it slows down. And that depends on the refractive index of water. The refractive index of water depends on things that you might guess: salinity, temperature, depth. So this didn't exist. So for the first time ever, we created this global refractive index layer. And I think it was Val that asked the question earlier. This refraction correction ends up moving your points up by about 25% of the water depth. So they go from here to here. And it moves it slightly horizontally. It moves it kind of in towards nadir. Another part of this, I mentioned earlier, this total propagated uncertain bathymetric lidar TPU tool, CBLU. Fortunately, this already existed through this collaboration between CCOM, my research group, and NOAA NGS. So we were able to leverage CBLU for doing the uncertainty modeling portion of ATL 24. So basically, CBLU breaks the uncertainty into two components. You've got an in-air component, or part of it's actually in space. This we didn't have to do because NASA had already done that for us. It's available in something called ATL03. And then this part was the Monte Carlo ray tracing. So we just got done with that. And you can see this is a cartoon, so we can't really evaluate where is half the water depth. I don't know. Maybe not. So is this going to solve the problem? Not completely. I wish it would. It's going to be a fantastic product. I'm really excited about it, but it's not going to completely solve the problem. It's just too large to do this globally, solve it everywhere. Again, some of the limitations I mentioned, we're just getting data along discrete track lines. We're limited to where water clarity is good, although with enough overpasses and another decade of operations, we'll have a lot of opportunities to hopefully catch some of these turbid areas at a good time. So, and I already talked about some of the challenges with boats and things you can do in situ. So what's the solution? I think it's putting everything together. We've got a lot of different technologies that can all map shallow nearshore waters. And kind of like when I was talking about the ensemble algorithm for classification, it's actually a good thing that these all work differently. They all have their strengths and weaknesses. So to me, the biggest thing that remains to be done is to work together to develop some really good fusion algorithms for taking all of these different technologies that have different resolutions, both spatially and temporally, and different accuracies, and be able to intelligently fuse these to solve this nearshore data void. And this leads to a project that I've been doing with Jen Dykstra for the past few years in the Florida Keys, where we're actually looking at doing this. Everything from ISAT-2 to airborne bathymetric lidar, drones, autonomous boats, and diver data that Jen and Glenna in the back have been doing a lot of the dives on. So really cool. I just have some quick fun photos. This is an Echo boat that we used 2 years ago. Some of the bathymetry collected from the Echo boat in these areas. We've also been doing some drone work. That's a PhD student, Selena Lambert. So this was Selena a couple of years ago collecting drone imagery, and then we've been processing the drone imagery a couple different ways. There's a couple ways you can get bathymetry out of the drone imagery. One is through stereo photogrammetry. So, and this can be done using structure for motion technologies so Jen uses AzureSoft Metashape for processing the underwater imagery. That's also fantastic for processing the drone imagery. There are a few other software packages. Pix4D is one that we use. And then the other thing that we can do, it's kind of interesting, but you can treat the drone imagery just like satellite imagery and do some of the spectrally derived bathymetry techniques. So Selena's first dissertation paper was taking the drone imagery, and you don't have to do this with satellites if they're nadir pointing. With drones, you have to account for the off nadir angle, or we called it a refraction correction. So she did a refraction correction. And then of course, Jen and Glenna doing the underwater work and then underwater photogrammetry. And the whole idea of this mode has been for many years, like a couple of decades, trying to produce coral that are going to be a little bit more heat resistant. and then do these outplanting of coral. The really bad news is last year there was record heat. So you might have seen this on the news, the water temperature on the Florida Keys got up to 101 degrees Fahrenheit. And I was talking to Jen yesterday, and Jen clarified that it wasn't even just that one spike. It was the fact that it was a sustained high temperatures over a long period. And I think nearly all the coral, maybe all the coral in there, I think Texas now. But it points to the importance of doing this, and I'm just looking, we yesterday had some images in her office. There are encouraging things through the research in terms of being able to sort of track. Now we've done this for enough years that we're really able to start tracking changes over time, and hopefully using those to point to things that can at least be part of the solution for the corals. Quickly, some related work done by some of my students. I mentioned Matt's bathymetric truthiness. We're also doing, this is, I don't know, do any of you remember Brian Medor? He was here too. So Brian is also a student with me now. So he's looking at bathymetric change using NOAA's SatBathy tool. Auto generation of seafloor reflections and waveform features. I've got another slide on this in a minute. I mentioned forest filling, missing SIT bathymetry, total propagated uncertainty. Those are all sort of related things. This one on the, so this is taking airborne bathymetric lidar and being able to create these seamless seafloor relative reflectance mosaics. So this is kind of like, if any of you have done acoustic backscatter calibration, kind of similar. You get the intensity data from the lidar, but it's messy and there's artifacts. So you've got to do some cleaning to create these nice mosaics. You can do this though, not just with the peak amplitude, but you can take any number of these waveform features. So you get back some received signal that looks something like this, and you can look at all these different shape-based features. So like its amplitude, its width, its skewness, is it landing one way or the other, its kurtosis. And we've come up with ways to generate these nice seamless mosaics. Ellery Olweiler, she got to fly on a NOAA plane last fall, so she was super excited to go fly on the plane and collect some data. All right, so finally, like next steps. Here's the immediate to-do list. We've got to finish ATL 24. Our goal for the first version of ATL 24 is the end of this summer. I say that both with some excitement and a fair amount of trepidation, but we are working very, very hard to get this first version done. So that's the SIT bathymetry project. Compiling longer and longer time series of SI2 bathymetry. Like I said, the mission has enough fuel for another decade. So really looking at opportunities to improve the density, improving the accuracy, and the big one here, develop, test, refine these optimal fusion strategies. So that's the short-ish term, maybe. How about the future? This is future us, right? Future us. Hooray, hooray. The global nearshore data void is so awesome. They just did a perfect of this. So the question then is then what? Like, great, now what do we do? Do we celebrate? Do we retire? What do you all think? The answer is no. Now we got to do it again. We got to do it again. The ultimate goal is not just to get to the point where we can do this once, it's to get to the point where we can do this every year or every 5, just keep doing it again and again, being able to understand nearshore morphological change, modeling storm surge vulnerabilities, climate impacts, future coastal policy decisions. Every time we've done a poll and we ask people, what do you want? Do you want like just one snapshot of very accurate bathymetry, or do you want bathymetric change over time? Bathymetric change over time always wins. That is the ultimate goal. Like I said, this is a big problem. I would very much like to collaborate with anyone here who's interested in working with me on this. Just wrapping up, I'd like to acknowledge some funding sources, and more than anything, I would like to acknowledge these amazing people here. These are my graduate students, past and present. Just some truly fantastic folks here. If you look, you might see some former CCOM folks there. And with that, since Larry said I had a bunch of time, did I eat up all the time?
I'll start. It's just a technical question. The rationale for the strong and weak beam on ISAT.
I think that had to do with the ice sheet monitoring, and I could be wrong on this, but the fact that for ice sheets, you know, they can be very bright, and so I think it was so that if you were going to get like a specular reflection that would possibly saturate, that you could have the weak beam that might give a.
Do you strictly use the strong beam or?
Oh, fantastic question. When we first started, I thought that I just assumed that we were going to use the strong beam because more energy, you're going to get deeper. Generally, that's true, but it's not true at all that we only get bathymetry in the strong beam. We can get bathymetry in the weak beams too. Occasionally it's better, almost always it's the strong beams that are better, but occasionally for whatever reason, the weak beam will give better bathymetry. But if we use both, then that's just increasing the area.
Can you back out optical attenuation?
Yes. So one of the first things that Forrest Corcoran did is he did a study to estimate KD. He did it using machine learning. So he had a random forest. Forrest had a random forest model that he used for estimating KD, diffuse attenuation coefficient. Since then, other people have done this, and Emily Idem, who is a professor in CEOS at OSU, has just done. She's just done a really comprehensive paper, also looking at KD estimation from us too.
So then for satellite dry bathymetry, you won't need to go out and measure it if you have
the attenuation coefficient in theory, yeah. Right, and that could be used for other things. I could go into a lot more detail, but
let other people ask questions.
Yeah, Jamie, right?
So yeah, you answered the question of what the resolution along the track is, but what's the whole cross?
Yeah, so the outer beams, if the center beams are here, the outer beams are 3.3 kilometers on the ground on either side. So you've got kind of this 3.3 kilometer gap, but sometimes you get, you know, multiple passes that come back around. So it can be, it's really variable. There's a site, if you want to just look at coverage, there's a site called Open Altimetry, and you can look at, oh, I forgot to mention something important. And this is going to relate to your question, something that Kim Lowell just volunteered to do. So in areas you can just look at what the track density is, and it's variable. You could get lucky and your area could have pretty good coverage, or you could see that there's maybe just like one pass through your area and then nothing. But, and I can't believe I forgot to even mention this toy that I brought, that I use this. I use a lot of toys in teaching. This is an important one. This is my Lego satellite. So believe it or not, so ISAT-2 can point, you can send a request to NASA and say, we want to point at this. We've got this high priority area. We want to point at that. The way they do it, I would have thought that it was like some form of beam steering, either through signal processing or like a rotating mirror or something like that. Any guesses as to how the satellite points at something if you ask it to? The whole thing, they just tilt the whole satellite, but they will do this. So you can submit these requests. And so Kim's been participating in our ISAT-2 bathymetry working group meetings, and is going to lead this study of our working group, where we're going to look at how we can sort of task the satellite to increase optimal density over priority coastal areas. So you know, what's going to be sort of the optimal strategy for trying to build up data. Some of it's going to happen naturally with another decade of operations, assuming nothing happens. You know, something else I found out, I went to an ISAT-2 meeting. I didn't know there were people whose job is to fly the satellite. Does anybody know that's a thing? And basically what they do is they keep it from hitting other stuff in space, including space junk. So I raised my hand and I said, well, if you didn't do that, how long would it be before you likely hit something? And the answer was not long at all, because apparently they need to constantly monitor these things. But anyway, I don't know where I was going with this, other than, so Kim's going to lead a study, and we're going to look at seeing if we can actually submit these requests and have them try to build up the density in priority sites. Wow, that was a long answer. Yeah, Val?
You said that each beam is 11 meters in diameter, roughly. I mean, does that change much, or is the geometry relative to the surface of the Earth such that that's pretty well constant? I guess it depends on what the topography is.
I don't know. One of the things that it depends on is where you even measure that. and multibeam would be the negative 3 dB points of the beam, and LiDAR, it's the equivalent thing would be like full width, half max, right?
Yeah.
Or that might be the 1/e² points. I know more about how it's measured than how, so the way that that's measured is there, so Lori Magruder, I mentioned, she's got this calibration facility at White Sands, and so she's got targets out there, and she can actually physically measure the width of the beam based on, I don't know where these targets are and what she's seeing within a footprint. I would assume the answer is it's somewhat variable.
So I have like, this was actually my question, that was just a side one, but if you had two surfaces, like a step change in the surface of the
Let me
earth.
resolve that. Like, what's the range resolution? Are you asking what the range resolution is?
No, well, maybe, but like presumably you go across it and you see a transition that's not as sharp as that step change is because the beam is 11 meters. And I guess my question is the fraction at any point of measurement as you go from sort of the further away to the shallower place proportional to the difference in area that you've illuminated that was deep versus shallow? Do you know what I'm asking?
So if you've got a sloped surface.
No, a step.
A step.
A step, so it's binary.
Yeah.
You're either, like half your beam is on the, like, if half of your beam was in the deep spot and half of your beam was in the shallow spot, would the detector, do you think, measure halfway between the two? And if a quarter was deep and 3/4 was shallow, maybe it would do 3/4 of the way to the shallow? Is that a silly question?
It's not a silly question. I don't know.
Curious.
I don't know the answer. You're getting all these different photon, so you can get many different like geolocated photon returns that might be that you would see some returns.
Now, if you had a multi-beam in that situation, what would happen? Same question.
I mean, you have 70 centimeters, so you're gonna average.
70 centimeters is the,
That's
between
the
samples.
That's between.
So you'll have multiple samples within the footprint.
I don't know. I mean,
have a single beam echosounder. You get just the top, right?
it depends, because if you do a depth weighted, if you do an amplitude weighted mean, you're gonna smear it across that.
Yeah.
And in this case, you're measuring very small number of photons.
Yeah. I mean, it's photon. So in theory, it's single photon sensitive. Maybe not quite at that level, but
So you,
a small number of for sure, a small number of photons.
so you start to see the effects of interference between the photons in a way that you don't maybe.
These are fantastic questions. I'm hesitant to say something that might be incorrect.
We can talk later.
Yeah. Jere.
That's related to what Val was saying, because every single point there is a photon event.
Right.
And this photo event is, the location is assigned to this point event, photon event. But do we really know where it happened? Where exactly, how accurately it is located?
Oh.
Because when we are talking about the footprint, at first it was 17 meters, then down to 14. Now we are talking about 11, which is, I don't really understand where it came from. But actually, it's not about footprint. It's about each single photon event, which is, you say, that's a truck, the photon event is here, and we take it as given, but
Well,
do we
for
know
sure.
the?
And I mean, some of those could be noise photons, or they could be. Some of them could be noise. It could be receiver noise. It could be atmospheric scattering. It could be
Sure,
scattering.
noise, but we are also relying on it to estimate the bathymetry and water surface, etc.
Yeah.
But in fact, do we really know where it happened?
I mean, the accuracy is quite good, and by doing averaging,
know
especially, how do I know? Well, there have been so the only studies I've done or looked at have been the bathymetric accuracy. But as far as like elevations on ice sheets, It's on the order of a few to several centimeters vertically, and that's been validated by people who've gone, so for example, Kelly Brunt at NASA and others have, they've gone out on the ice and done GNSS surveys along huge tracks and
Yeah, well,
compared
if
this.
it's on a centimeter level, that's pretty good.
And a lot of it is by averaging, and they really need that. I mean, the primary mission again is looking at ice sheet elevations. And if, I was talking to Jen or Kim or somebody, if you're off by a little, if you've got a bias, and then that's propagated over, let's say, the entire Greenland ice sheet, you're gonna get a completely different answer. So people have really worked hard to try to remove systematic errors and to get that vertical positioning uncertainty as tight as they can.
How, the actual laser, so you say it's 11-meter footprint when it hits the water surface. What's the size? What's it start out at? I'm just trying to understand how much it spreads over however many thousands or hundreds of kilometers.
I don't know the answer to that either, but I'm assuming it's tiny. The person who knows, Tony Martino, is a systems engineer at NASA, and when I have a question like that, that's who I ask. I'm assuming it starts out like centimeter-ish size and expands. I mean, and the beam divergence is, I think, quite small, but you're going 500 kilometers.
Chris, did you hear me?
Yes.
One question about the final results. So there is
Jere?
Victor Fagels. There is IHO standards. So how you connected with IHO standards? What type of measurements? So class A, class B, special order. What kind of order can be in this method?
How does it relate to IHO S44 survey orders? Is that the question?
Correct.
Wow, you are really, these are fantastic questions. So IHO, let's see, we've got special order, IHO S44. The current edition is the 6th edition of that. Am I correct?
Yes.
Correct me if I'm wrong. So we've got special order, order 1A, order 1B, order 2. Order 1A and 1B, the vertical uncertainty is the same, and it's the square root of 0.5 plus 0.025.
Squared plus d squared.
0.13. It's about 1.3%.
It's on. I have made no claims, so I don't think we're meeting 1A/1B. I feel pretty good saying that we're meeting order 2. Possibly, and I don't know, once we've got a lot of work to do. I've got a ton to do in the next few months, but once we produce this ATL24 product, we're gonna have a lot of work that I'm gonna try to get done over the summer and validating it. And one of the things I wanna do is not really believe what people have said in the past, but take our first ATL24 run and really validate it using all existing multibeam airborne bathymetric lidar, things that I trust, and see how well we do. I would be very hesitant to say order 1A or 1B, which vertically are the same. I think I would say we're probably approaching that, but I'd be hesitant to put a stamp on it. Does that answer the question?
Yes, 100%. And you discuss the beam size on the surface. So sometimes extremely important to say for what level, because if to count scattering on the atmosphere, so in this case the diameter of the beam will be very big from altitude for 50 hundreds kilometers. But for the level, say 0.5, it will be much less. About the footprint size on the bottom. So I did some calculation for the bathymetrical LiDAR system. It's variable. It depends on field of view of your receiver, divergence of the beam, plus what is extremely important for the scattering on the forward direction and form of the water phase function. So that is, but remember about the forward scattering, that is important. Plus type of the bottom, because one result will be for the coral sand, another one for mud. So, but very variable. So diameter of the laser beam on the depth, say 10 meters for the Mississippi, for the Mexican Gulf water in the region of Mississippi will be huge, much more than the diameter of the 20 or 30 meters in Fort Lauderdale water. So we have the practical results in Teledyne. And Chris, personal question, why you do not use SysMil data? Something principle?
Why don't I, we do use SysMil, we do use SysMil data. We use a lot of, we use SysMil data quite frequently.
But in your list, in your slide, I see only Regal and Caraptera.
Oh, we have it, you're talking about SysMil. We have it, yeah, we've got Regal, VQ8, ADG. It's done. SysMil is done. We just haven't, there's one more thing that has to happen and then we'll add it to the list. That's the Teledyne Optech SysMil system. Yeah, check back in maybe 3 weeks. The SysMil is on GitHub. So check in about 3 weeks and SysMil should be there.
Okay. If you will have questions about SysMil, you can contact me directly. So you know
Sounds good.
my email. Okay. But thank you, Chris, for presentation. Very nice, very interesting.
Thanks. Others, we're probably, Larry said I had all the time in the world, but we're probably like 15 minutes past.
Do you have any online questions? No? Anyone else? Girl sets.
All right.
Thank
all
you so much.